Hey guys, I wanted to make a quick video here introducing you guys to linear regression. Typically in other classes when I teach linear regression, I teach it along with in the context of statistics. However, for this class, I like to teach it right after linear transformation because it kind of ties in the whole idea of why you might want to do some type of linear transformation to your data set if it's in a non-linear form. Okay, so here I have a set of data in which I have uh, a couple of measurements taken at different time intervals of the concentration of the single species A. So we start at the first measurement at 20, at 8.7, 2.6, 1.5, 1.3. All right, and our concentration of the single species given at any particular point in time is given to us by this nonlinear equation. So this equation here, this series of equation is our nonlinear data, right? And if I were to plot this data, all right, as a function of the concentration versus the time, all right, I would see that my data points would fall like this, all right. And we've done this in our Excel labs before the break. And if I were to get a best fit line here, all right, and look at the regression line or get a regression equation for this data set, which is what is plotted on the dotted lines here, all right, I can see that my equation is y equals negative 4.46 x plus 20.2, okay? And so what does this equation mean, all right, to us? All right, well, this is our linear equation. This is what this line represents. This is the actual dotted line that we see on this graph, all right, where 20.2, all right, this value here is our y-intercept, okay, all right, and that's where the line will cross the y-axis. So we expect the line to cross the y-axis at approximately 20.2, all right? And negative 4.46, all right? So the slope, this is negative 4.46 is our slope of our line, or this guy here. And what that means is that for every 4.46 seconds, all right, we can expect our concentration to go down by 1 unit if we were to use this line as a prediction. So that's what linear regression is it is taking a best fit line to create a prediction interval, okay? And so if we were to want to run this experiment again in the future, right, and we wanted to know where we would expect this concentration to fall, all right, at say, 3.25 seconds or so, all right, then we can use this linear regression line to estimate or guess at where we would expect that concentration to fall, all right. And then there's a couple other values that we can get as well from the linear regression, all right. And then this is this R squared value, all right? And you always hear about the R squared values, all right? And these typically talk about the variation, all right, of our data, all right? And so this means that 78% of the variation in the concentration is due to the actual time variable, okay? And so when you usually do this, I always say you want to get this, we want this as close to 100% as possible because we would like to say that, 100% of the variation in our concentration is due to that time variable. However, at 0.78 R squared value, this is not always a very good fit. This means that our, uh, you know, for our slope, for our regression line here, um, there, all of the variability isn't wrapped up in just this line. So there's some play here. All right. So we got a poor R squared value. All right. And so what I've also given you guys here, all right, in this next graph, all right, is the linear form of this. So if I were to take this equation, all right, and to actually plot a linear form of this, so now I've taken this and I've plotted, got a linear equation, all right, where our t is still our, all right, x value, all right, is still going to be x. However, now instead of plotting the concentration of A as our y value, we're now going to plot the natural log of the concentration as our y value. All right. And if I were to create a plot where I'm looking at the natural log, all right, of our concentration on the y-axis versus our time on the x-axis, now I can see, all right, and I draw a best fit line here for our new data, okay? And I get a new equation, all right, where y is equal to negative 0.72x plus 3.52. It still means the same thing, all right? Our y-intercept is going to take place somewhere around 3.52, all right? And now here, a negative 0.72 means, all right, that for every 0.2 or 72 seconds, we can expect the natural log of the concentration to go down, all right, by a, a single point, right, by one unit. All right, and so the cool part about this is that now if we're looking at the variability of our data, I can look at the R squared value in my new linear data here and see that I get a 0.93, which is a large improvement over 0.78, all right? And so now I've done a lot better at describing the variability in this data set, all right? And so I can say that at least 93% of the data or the variability in the concentration or the natural log of the concentration is due to the time here, all right? And so in the next video, I want to show you guys how we can do this, all right? So I did this in Excel, all right? But in the next video, I'm going to show you guys how we can get these values, all right, using our TI-84 graphing calculators, all right? Cool.